So we're going to have a bear walking the plank. And this plank is attached to something. So it's got, you know, this force coming in like that, the force up like that. So it's attached to something. And yeah, we're just going to pretend that I drew this well the first time. This is a mass, I'm sorry, a beam with evenly distributed mass. So what do we have? We're going to send a bear out there some unknown distance. And what we want to know is how far out can the bear go on this thing before it rotates? And we know that it's attached by this cable that has this tension T. Are we given the tension? Yes, we are. So tension is 900 newtons. So it has this tension T. So there's going to be an X and Y component. Let's just call this, what is this, 60 degrees. But I don't know that we need the X and the Y. Let's see. Let's see what we need. Let's just start with torques, because I'm going to start with this being the rotation point. And let's see, here I've written down the mass of the beam. So we're told that the beam is 6 meters long total and has a weight of 200 newtons. So these guys are going down, that one is going up. So I'm just going to go ahead and do the sum of my torques. The bear, let's see, the force of the bear coming down, actually let's do the one up first. So I'll go up is positive. So I have tension times sine of 60. Remind ourselves, torque is F sine theta, FR sine theta. So FR sine theta, so tension is what, the total length of this thing, so times 6 meters. That's the only upward force I have. So now I'm going minus the bear. The bear weighs 700 newtons. All of its force is straight down, so it's just sine of 90, so 1. So I don't need to worry about the sine, the trig function, but I do need to worry about the distance, and that thing is the thing we don't know. So some distance r from that pivot point. Remember, I'm making that my pivot point. Then minus, let's see, the mass, or the weight of the beam is this 200 newtons, that's the force part, times, well, if it's 6 meters long, it's evenly distributed, so it's going to be times 3 meters. And then the last thing is then minus these goodies, which is 80 then times 6 meters away. So this is 80 newtons times the 6 meters away the goodies are. And all of that, if this stays static, equals 0. So what this will give me is this distance here that I can go before I no longer equal 0. So what I'm going to do is move all my negative pieces to the other side. Actually, I know this, I know this. So the only thing I'm going to move to the other side is this 700 newtons because it has a variable. So I have T sine, let's go ahead and put the numbers in there. I have 700 newtons times sine 60. I'll go 6 times that times sine of 60. There we go. Minus this one, 200 newtons times 3 meters. Minus my 80 times 6 meters will equal, now I'm moving that piece over to the other side, 700 newtons times this x distance, that one we don't know. And then when I crunch this all out, I'm going to move, the last step then is dividing by that 700, and I just don't feel like writing this again right now. So this is going to be divided by that 700 newtons to solve for that. So let's just show that that's what we're doing. That cancels out, becomes 1. So then x, how far out can it go? 5.14 meters. Oh, that's so sad. Because the goodies are 6 meters out. So the bear is just going to barely get its little paw there trying to reach the goodies, and it'll never get there. Or the whole thing falls. Maybe he catches it, it's not up too high, so you can get the goodies before, or when they fall on the ground.